Happy holidays, everyone. It's great to be here one more time. Got a nice full house. And I tried to pick a fun topic for you guys this evening. It's a holiday party. So the topic is fun and games with a bunch of algorithms snuck in just for extra pleasure. There you go. Here, I'll give you that one. A couple thoughts before I get started. I thought the lightning talks were just extraordinary tonight. Let's give a round of applause to the lightning talk speakers. Christina's talk with Kepler in space makes her one of the people I want to talk to right after. If you're also interested in space, one of my good friends, Brandon Craig Rhodes, is here. Another interesting person to talk to. Go find him. And my nomination for Best GIFs in a Lightning Talk goes to Lizzie. Those were cool. A very elegant presentation. And Grant, I love the holiday theme. If you get a chance tonight, another couple people to talk to are Brian and Hala. They're here with a group called Being Heard. They're putting together a social network for the homeless. And they are looking for you. Tonight they are looking for a technical co-founder. So if you would like to be in a startup, one of the 3 co-founders of a company, go talk to them right afterwards. But most importantly, thank you to Yelp for hosting this again and making all of this possible. You ready to rock and roll? Good. All right. In preparation for this, I looked around to see how many of you filled out the puzzles. Did you see the puzzles laying around? There's a puzzle theme, hence the puzzles. A Sudoku and a word search. Now, these puzzles might look easy to you, but some of them are especially challenging because the designer doesn't think like you do. So, one thing that you might expect for things in a house is a telescope. The hint is something that you use at nighttime to look for planets. Easy enough. How about this one? Something that pops. Can you imagine what that is? Oh, that would have been a good one, but my son picked, that was the hint for balloon. So this is a puzzle of my son's design, as is the other one that you just saw a moment ago from his game, Busytown. So we picked all of the images there, and he would tell me where the word would go and what to cross it with. And my challenge was to turn this into a real puzzle as fast as he could say, no, don't put it there. Now go put it over there. Go put it over there. So I will show off a use of Jupyter notebooks for entertaining your children and building crossword puzzles. And so you can have clues like, I can fly a blank. It would be a kite. All right. So that's part of where we're going tonight. And that's just the playful part, showing what can be done with the Jupyter notebook and what Daddy made for his boy when I was on the way back from a training class. You fly cross country, you got your laptop open, going to see your son, you build a Jupyter notebook. That said, I've got other things for you this evening. On the way out here, I tried to put a lot of effort into the slides tonight, and the effort was cutting back on all the material I promised you. On the way out, I realized I have about 2 days worth of material to go over, and apparently I have to put it into 1 hour. So here's the overview. If you don't know who I am, that's me. If you don't know where you are, this is here. What do? I train programmers. Where can you call me? Notice how I use the clever dot convention so that you can't spam me. That's my company. The videos that were just auctioned off here are the Safari Online lessons. And we'll do a little overview. And what I've got for you is some depth-first and breadth-first search. Not terribly difficult, but these tools are individually easy to code in Python, but very powerful in what you can accomplish with them. Something that not enough people know about is SAT solvers. If you went to school many years ago, they didn't tell you about SAT solvers because to the extent that we had them, they weren't very good. Something miraculous has happened in our millennium. They've gotten very, very good. And an exponentially hard problem has become solvable or tractable for an amazing number of problems. So we'll do some SAT solvers. and pattern recognition and reinforcement learning put to noble purposes like how to win at rock, paper, scissors. All right, that's my plan. That's where we're going. This is the professional-looking part of the presentation to try and be as good as the lightning talker tonight. But we will start with the less professional part, which is, or less professional looking, which is what can you put together with a Jupyter notebook, and when do you want to code with a Jupyter notebook? And I think as an interactive environment, it's really impressive what can be done. So this is the goal, by the way, this is the output of what we're about to make. By the way, everything that you see tonight, I'm going to give you all the code for the Jupyter notebooks so that you can go do for your children what I have done, and so that you can win at rock, paper, scissors over Christmas, and so that you can put your machine learning tools to use to save the earth. All right, here we go. My crossword puzzle generator. Making a grid. Very few data structures involved. The grid I decided to store in a dictionary. The reason for this being in a dictionary is the kind of crossword puzzles that my son was working on were sparse crossword puzzles. They're not the dense ones like the ones in the New York Times crossword puzzles. So a dictionary is more suitable for a sparse data structure. Also, dictionaries are really handy to code with. If you code with list or with matrices, you don't get keys, values, items, things like that. So that'll be really handy for us. I have a set of all of the starting points for a word. So once you place a word on a grid, you need to know where that word started. And a dictionary of hints. Given a row, and column, and direction, find a hint. Hey, notice new type annotations here. So one of the things I like about the new type annotations for Python is even if you don't use MyPy and make the type annotations run for you and check anything, they're actually a great documentation tool. It says, what is the key to this dictionary? It's a tuple, and the tuple has a row and column, and what direction it is. The direction is important because you can have at a given grid point something going down and something going across. And the output is a hint, which is a string. I love this as a documentation technique, and so even when I'm not using MyPy for type checking, I'm still using the type annotations. And then a dictionary that translates a word, given a word, go back to its coordinates so that we can find it on the graph. This is really helpful when we print out the grid. So the very first operation I came up with, and you're seeing this in the order that I experimented with it. So I wrote MakeGrid, and then I tried it out to see if it worked. The very next one is assign. At a given row and column, place a letter. And the only error checking here is it tells you if that place is already occupied. So that's enough to put letters in a crossword puzzle. The next level up is place. Place is the idea is I built on top of assign, which assigns a letter, and I want to place an entire word. So where does this word go on a particular row and column, and a direction. It was really fun to use place for the first 1 minute of using it. And it turned out that this is a really irritating API. So how are great APIs invented? It's easy. Dog fooding. Be your own first user. I used place for about 10 minutes. And at the end of that, we invented cross. And cross is is something that saved me an enormous amount of time, particularly when I knew in advance from the puzzles that my son had already made where some of the coordinates were going to go. So I had that in mind here. But the moment that you start designing a new crossword puzzle in front of a 6-year-old boy, they'll say, no, I want the word over there. And if you have to count over, this is row 14, column 5, they've already lost interest by the time you've gotten there. So cross says take a new word, cross it with a old word. So if you have a word that's already on there, say place the word kites across traffic lights, and it will intersect them for you. The problem is there's multiple intersection points, and I needed a way to communicate to it where to cross. So I invented a new domain-specific language. That's what you should always do when faced with a new problem. It's not a terribly difficult DSL, but the idea is I put a capital letter at a cross point, and it's a hint to it where to go. It still keeps it very natural language looking. So not a lot of magic here. If it's a cross, draw it across. Otherwise, draw it down. And essentially, it's a front end for place. Afterwards, I realized I needed to generate the clue numbers once all of the pieces were on the puzzle. My son liked to assign the clue numbers as he went along, but it would occasionally put new clues up above the old ones, which would cause everything to renumber. Sounds like work for a computer, don't you think? Hence a very small generator with a enumerate. And lastly, we organize the hints to print them out. So here is and then I needed a way to look at it, so I made a small show grid function that looped over the grid. So here was an example. I probably ought to run this notebook real quick. There. All right. And which, of course, puts me at the bottom, which is not where I want to be. All right. We are in MakeGrid. We've said make a grid. The very first word you actually have to place and tell it where to go. So at row 1, column 2, and the hint for hello is aloha in English. That's my son's hint, by the way. Control Z. There you go. All right, but the next one is more interesting. When we place the word red, I capitalize the E, and that says cross it with the E in hello. If there are 2 E's in hello, it'll choose the first one. If I want the second one, I'll capitalize the second letter. The idea was to make this easy to type in, and as fast as my son could change his mind on where to cross it and what the hint was, I could enter it, and presto, there is hello crossed with red, and we've generated the hints, the across hints, and the down hints. Then he says, I want the word books, and I ask where it goes. And books crosses hello. Now, books has 2 O's in it. How do I indicate which O? Capital letter. Hey, people paying attention. $5. Okay, and presto, there is books. And it would draw, and then he decided whether he liked it there or not. Then cleanest. And then because you can tell that a computer programmer was involved in putting an extra example as I was driving up here, keyword in context, quick index, not in my son's vocabulary yet. That would be next year, 2nd grade. And along the way, it's renumbering all of the hints. That's my Jupyter notebook. Awesome? Yes. No, we haven't tested to see if it would scale yet. You have to see if it scales. Hence, the Busytown. All right, MakeGrid. Kites at 0, 1. I can fly a blank. Traffic lights cross the I with the I in kites. Traffic lights apparently are found at an intersection. Shovels digs holes, and clocks are things that tells time. Some of these, though, it's just interesting. An anchor is a thing that ties a boat. I would not have described it that way. And flags, something that has 50 stars. All right, there you go. And we run it, and presto, there's the Busytown puzzle. There's only one problem with the Busytown puzzle. It looks terrible. What part should you save for last in your design? The temptation is to make it beautiful first, but always get your core logic correct first. Testing text-based let me iterate very, very quickly. If I wanted to cripple myself, I would have tried to make it look beautiful first. So only after all of that worked, a little scalable vector graphics with a little style sheet and a little bit of templating, and the puzzle now renders this way. There's only one problem. What's missing? The answers. Well, of course, it's a puzzle. You can't give people the answers at the outside set unless you set display equal to true. And now the answers run it. So I could print the puzzles with the question and the answer. But you have to know how to drive a Jupyter notebook to use it, and you can't use your favorite editor, VI, Emacs, TextMate, Ed, Atom. So we need to go further with our DSL. By the way, these are lots of puzzles that he got interested in making afterwards. Theme, clothes, daddy's friends, our family, etc. So here's a part that is incomplete right now in that I haven't made it to where it can take in files. But this is a specification for a puzzle. So it allows comments. This is pretty easy. You do a split lines and ignore any line that starts with a comment. There's some tags, indicate the theme that will go at the top, where the initial start is, the location and direction. So Papa blank, Papa Haydn is the answer. And then after that, the DSL makes it really easy to type in crossword puzzles. So Nana crosses Papa, and the hint was rhymes with banana. Papa and banana don't actually rhyme, but that was the clue, and that's what makes these puzzles tough. To-dos, it needs a topological sort so that you don't have a dependency in it, so that you can throw these things in out of order. That will make it a little bit easier to use. So the topological sort is starting down here, and the testing code for it is to shuffle it and see if it can still build. So I've yet to package that part up, but I'll wrap all of that up so that there's a standalone tool as well as a Jupyter notebook. I can't think of any other way to have built this productively without the Jupyter notebook, so I'm now count me as a huge fan. Anyway, that's my puzzle maker. My son loves it. I hope you love it too. I will give you this, and you can play with it. The Epiphany. The Epiphany was this. In order to get all of the green squares, I had to mark loop over all of the values that were filled in and count them as being somehow different. And so for the style sheet, I told it to change the color and to suppress rendering of a letter. And that's when it hit me. I don't have to put green squares in here. I can put letters in. So here I am at 54 years old, and I finally realized that these two puzzles are isomorphic. That in fact, if you take out all of the black squares and you put in other letters, you've got a word search. So the very next step is, next time I'm trapped on an airplane for an hour, we will put in a random number generator for letters, and instead of green squares, generate word searches from exactly the same puzzle. I finally figured out the two are the same. There you go. Oh, and the one I didn't figure out, someone had to tell me. You only find this out when you have a young kid. You know the song, the ABC song? A, B, C, D. You know the song, Twinkle, Twinkle, Little Star? Did you know that they're the same song? Note for note? Isomorphic. So where we are is crossword puzzles are isomorphic with word searches, and Jupyter notebooks are awesome. All right, next one up, the serious stuff. BreadthFirst Search. Let's make it big. All right, lots of puzzles can be solved by BreadthFirst Search or DepthFirst Search. I say lots of puzzles. I might even dare to say most puzzles. So I have a list of about 20 puzzles I have solved with this tool, and I published it a long time ago, but in a place where no one could find it, and so this is a hardly used tool, but it's really fun to work with. What I'm going to develop here is a generic puzzle solving framework where that lets you specify a puzzle and then solves them all. So what makes it easy is collections deck. Deck is the double-ended queue. And so I'll give you a generic puzzle solver. By the way, I skipped the overview. I should quickly do the overview. All right. What to keep in mind as we explore. What you're looking for is in each of these examples how little code it takes to solve each fairly rich problem set. Also, another thing to look for is each time we solve one of the puzzles, we make it generic so it can apply to something very broad. And so I think this is a good general design pattern. We start with toy fun problems, but I'd like you to try and stretch your imagination a bit. Every one of these tools can be applied to work problems and more practical applications. So, but in the spirit of Christmas, it's all fun and games here, but go put the tools to work somewhere else. I'm giving you this toolkit. Some of the tools needed a front end for them to make them easier to use. I'm giving you that as well. So here's the core idea for describing a puzzle so that we can solve it. We need to know only three things. What is the initial position of a puzzle? Second, we need some rule, usually an iterator, that generates from this position what are all possible moves. So think of a game of chess. You come to a chessboard and it's set up in a certain way, and an iterator will list out all possible moves that you can make that are one move away. And then we need a way to recognize the goal state. Have you checkmated your opponent? It turns out those are all the inputs we need to solve a problem. There's a couple extras that we can add on. The internal representation of the puzzle and the way you want to think about it might be different, so we'll add a nice repr method to make it look pretty. And some puzzles have lots of positions that come up in several different ways but are equivalent to each other. So in tic-tac-toe, if someone's first move is the upper left corner, it's effectively the same game as if they had played in the lower right-hand corner. So we can speed up the process, make it more memory efficient by having a function called canonical that says, these several positions, here's the canonical position, have you seen it before? And that'll speed up your search. So here's a simple example, the jug filling problem. So you've got this jug with 8 ounces of water. You've got a 5-ounce jug, a 3-ounce. And the problem statement is, given these jugs, see if you can find a sequence of pours that leaves 4 liters in the 2 largest jugs. So 4 liters here, 4 liters here. Notice how this is a really, really challenging problem. How many of you think you could solve this problem with these jugs? It's unsolvable because I had to put the problem statement in liters and these jugs are measured in ounces. You could not solve the problem. Trick question. All right. So, how to code the problem. So, this is all of the code for the problem using the puzzle solving framework. We'll see the framework in a moment, but I'll show you how to use it first. So we subclass puzzle, and one thing we need to tell it is what is the initial position. 0 ounces, 0 ounces, and 8 ounces. What are the capacities of the 3 jugs? 3, 5, and 8. And what is the goal? 0, 4, and 4. The only other thing we need is an iterator that says in a position, can you yield new puzzle problems that says I have done a pour of from the initial position. So here's how that puzzle instance works. We make an instance of a jug fill, and I print it. This one doesn't have a particularly cute repr. If I wanted to make a really nice repr, I'd draw the jugs with water in them. Okay, so it starts at 008. I can ask the question, is this the goal state? No, that's not the goal. And I can iterate from that position, and here are the 2 places you can get. You can pour the 8 ounce into the 3 ounce, leaving 5, or you could pour the 8 ounce into the 5 ounce, leaving 3. Okay, but if you run the solve method, here's the cool part. With only that little bit of code above, you ask solve, and it just spits out the answer. Here's the sequence of pours. And that's not terribly interesting because this problem is so simple. What is interesting is that using the same little code, you could solve much, much harder puzzles. So this is a puzzle that I had solved before and I had thought was easy. I'd like to take you one that I hadn't solved before and that I didn't consider easy, and that is the sliding block puzzle. So this exact puzzle, except it had white pieces and a plastic outline, was at my grandfather's house, so I call this the paw puzzle. And it sat around his house, and my father's an engineer. My grandfather was an engineer, and all of his friends were engineers, and people who came over the house were engineers. And when engineers come over to the house and see a puzzle, what do? No, they attempt to solve it. I have seen grown men and women who are very smart after an hour throw this puzzle across the room. No adult I have ever met, ever, has solved this puzzle. What do you need to do? You need to slide it, and you take this big block and move it down to the lower left. I have never seen a person ever solve this problem. Would you like to know why they haven't solved it? You might think because there's no solution, but it turns out the solution space branches out quite a bit, and then there's a keyhole. And if you're in that particular place, there's a move you can make that takes you to another search space. It balloons out again. And if you pass up that keyhole, you can sit there shuffling around all day long and not get into the second group. Once you're in the second group, it expands out quite a bit. You shuffle around. You can accidentally end back up in the first batch. Or if you hit another keyhole, you can go into the third batch, at which point sliding it is somewhat easy. Also, the sequence of moves is not small. I think the smallest or shortest path on this was something about like 95 moves. This puzzle is dramatically harder than it looks. The only person I know in the world to have ever solved this puzzle was me. And I solved it when I was 12 years old. Would you like to know how?
Pick it apart.
That is a possible solution, not a fair game solution, but in fact, taking it apart is a solution. Z80 processor was harnessed by Radio Shack to make a TRS-80 8-bit computer, and I wrote a little program in BASIC that you're now about to see in Python that solved it lickety-split. So it looks far more beautiful, by the way, in Python. So the paw puzzle, how do you code it? So I have a description of the puzzle, and the initial state is written like this. This is not how we think of it. We think of it like this. So block number 1 is of size 4, and here's its position in the upper left. Our goal is to have it down here. But it's easier to put that in row major order, smush it all together, and store one position as a single string. By the way, if you have a whole series of these strings printed out, is it going to look very nice? No. So what do we need? A repr. And all the repr does is loop over this string and produces that block. Could have made it look prettier, but that wasn't the goal. Now we need a way to recognize the goal. And the goal is we need to have a 1 right here. There were a number of ways to do that, but the easiest way, shockingly enough, was a regular expression. I thought I'd never say those words. All right, so is it a goal? And we'll search and see, is there a 1 in this position? And if block number 1 made it there. So canonical uses a string translate to map all of the isomorphic pieces to one another. So it turns out if you get these two pieces swapped with each other, to you it looks the same and is the same puzzle. But to the machine, they are two different blocks. So what isCanonical does is says if these two blocks get swapped, it's the same position, and it keeps us exploring the same one twice. When I had attempted to solve the puzzle manually, I did figure out that that was a problem, and actually put a little colored sticky on each of these so I'd recognize when I got to a position that I'd done before and recognize a dead end. So we describe the shape of the puzzle, where the blocks are, and make an iterator that says, given a state of the puzzle, iterate what are the possible moves. So in this case of the initial position, one move is to take the big block down, and the next other possible move is to take this block up by 1. If you take it up by 1, that opens only one new possibility to slide this one up, and there's a chain of operations that you can do either way around. This is 100% of the code necessary to solve the puzzle, and the output looks like this. Here's the initial state, here's the first move, and then I clipped another 80 moves, or 90 or so, and then finally it ends up here. So if you have a problem you can't solve yourself, get a computer to do it for you. That's what they're for. So the essential logic is basically this. You need collections deck, which is a double-ended queue. So for a BreadthFirst search, what we do is we pop off an unexplored position, something that we've never seen before. We pop it off the queue, and we generate the next possible moves. For BreadthFirst search, where we put them is we pre-pin them onto the queue. In other words, if we get some new moves, we don't explore them right away. We put them fairly far into the future. So we're popping off the right side, pre-pinning on the left. For a depth-first search, we append rather than prepend. That way we're appending on the right and popping on the left so that as soon as we generate a new move, we explore it right away. There are some problems to where you wiggle around until you get an answer, and a BreadthFirst search gets wide too quick. On a puzzle like this, we really want BreadthFirst. Otherwise, the answer would be, oh, here's a sequence of 2,000 moves that get you to the answer. It's the first one the machine encountered, but it's not actually the shortest move. So for this particular problem, we'll want BreadthFirst Search. A data structure that we're going to need is called a trail dictionary, and all it does is map each move to its predecessor. How did I get here? The idea is that we have a predecessor chain. Once we've solved the puzzle, we can answer the important question, how did we get here? Keeping a record of where we went along. And then the optimization I mentioned before is the user-supplied method, canonical. It says, are there two board positions that have different numbers on them, but are in fact the same board position? So here's basically 100% of the logic of the solver. So we take the initial position. While we're not at the goal, loop over. Where can we get to from here? For each move, we canonicalize that position. Say, have I seen it before? If I have seen it before, keep on exploring. Otherwise, add it to the trail and load it onto the deck. The interesting part about load is that if we're in a depth first mode, it appends. And if we are in a breadth first mode, it appends to the left. So that's my generic puzzle solver. I have ones that solve a triangle T puzzle and various Marvel puzzles and whatnot. I'll publish all that code for you with the worked out solutions for each one. And the challenge playing with this is it's not the solution part that's difficult. The part that takes your attention is how do I represent the puzzle in Python? How do I represent a goal state? And how do I make an iterator? And for some games, the iterators are quite complex. Like having it solve chess in games was something that I solved with this. And so I had to put in all the moves of chess, and the goal state was checkmate. You would do a breadth-first search on it, and the typical chess problems would say white to make a mate in 4 moves. And the harder part of that is the little combinatoric explosion of black can do anything. It has an adversarial role. So if you'd like to have a little fun these holidays, take my generic puzzle solver, which I'm giving you, find some puzzle, and spend a few minutes in Python making a solution to it. I love this thing because it is so generic. It is very, very few lines of code, and yet it solves a broad class of problems. We're done with depth first search.
No, you're not.
Oh, I am.
Your goal could be simplified with substring.
Oh, and so it could. And so it could. Premature optimization is the root of all excellent ways to spend time during the holidays. All right. Okay. Some of you are algorithmically sophisticated, and, well, I would say probably most of you because of where I'm speaking tonight, and are unimpressed with depth first search and breadth first search because you've done one of those before. So let me take you to a tool that not enough of you have used, SAT solvers. How many of you even know what a SAT solver is? Oh, then I'll start at the beginning. How many of you know what a SAT solver is and think they're awesome? I see. We will cure both of those problems. SAT solvers. SAT solver is a tool for finding solutions to problems that can be specified using propositional logic formulas. Any questions? Exactly what I was thinking about. So, propositional logic, A and B implies C, that sort of thing that you'd played around with in school and probably don't use a whole lot on a day-to-day basis. So the question is, how often in life do you have a propositional logic formula and need to find a solution to it? Does that come up much? Surprisingly, the answer is it comes up a lot. The reason that it didn't come up a lot before is that they're hard to solve by hand, and most of these problems that we could solve by hand had a more efficient way to do them. What makes them awesome is that they scale to very complex problems that have no more efficient solution, and it's as easy to code complex problems as it is simple problems. So I'd like to take you through a simple one, slightly more complex, and slightly more complex after that. So here we go. So this is an example from a math professor. He said, problem statement. If the tire is flat, I will have to remove it and take it to a gas station. Your first step is to translate each statement into a variable. So P means the tire is flat, Q means I have to remove the tire, and R means I have to take the tire to a gas station. Of course, you can simplify all problems by putting in mathematical variables and putting in mathematical logic and losing track of what you're talking about. Okay. So we write it in symbolic form. P implies Q or R. So that's a direct translation of that statement. The student exercise that they would give you on an exam in first semester logic class is to make a truth statement, truth table for it. So here's the 8 possible values of P, Q, and R, and then here's the validity of that statement. You'll see that 1, 2, 3, 4, 5 of these are true. That is a really, really easy exercise. So we say that this equation is satisfiable and it has 5 solutions. It's not seeming awesome so far because this is a trivial problem. Now, if you put in a few more variables, how many rows did I have here? Well, with 3 variables, 2 to the 3rd power is 8. With 10 variables, you have 1,000 rows. 20 variables, 1,000,000. 30 variables, 1,000,000,000,000. Do you see a problem here? There are very common problems that people want to solve that have thousands and tens of thousands of variables. Do you think this is going to scale very well? Just make a truth table and find the rows that are true. Hence, we get SAT solvers. What does a SAT solver do? We say it's satisfiable if one row is true. And a SAT solver not only tells you whether it's satisfiable, it generates at least one, possibly all of the rows that evaluate to true. There are some problems for which it's a miracle if you get even one solution. So why do we care? The reason that we care is this type of logic that didn't scale very well at one point suddenly got fairly easy for modern computers. And it's not because the computers got more powerful. It's because the algorithms and heuristics have gotten really good. They can't explore the entire search space, but they've gotten really good at narrowing down the problem for lots of real problems. So the miracle is that these things work at all. And they work very, very well, and the technology is improving quite quickly. There's a broad class of problems that didn't used to be solvable that are now easy to do. So here's the tools available. In the Python world, we have a third-party package called PicotSat, not in the standard library, and it's a front end for a C library called PicotSat, which is very, very popular in the SAT world. So, it's kind of late. Should I get technical on you? Of course. I can say with a straight face, conjunctive normal form. You need to write it in conjunctive normal form. Whatever you do, before you can go anywhere, you need to write in conjunctive normal form. Interestingly, my spell checker even knew the word conjunctive, but it didn't know the word disjunction, which surprised me earlier. So it's a product of sums. So a way to write that formula that we had before is this. Not P, R, Q, and not P, R, R. One of the interesting things to me is that this is a completely unintuitive formula. It doesn't seem at all like the one that describes the flat tire situation. And so I've found that people don't think in conjunctive normal form, but that's the input to the SAT solvers. It's what it requires. Worse, PicotSat has a terrible input format. So our variable P would be written as 1. Why? Because it's the first variable. What do you think Q would be written as? 2. Oh, and R? 3. Now, how do you put in not P? You use a minus sign in front of it. So -1 means not P. So the input to PicotSat if this equation is the -1, 2 means not P, RQ. And what must also be true is not P, RR. Does this look at all like our original problem? No. So it's hard to reason about, and its output is in its own format of all of the -1s, but you'll recognize here are the 5 solutions that we saw earlier with the truth table. Unimpressive so far because you could do this by hand. Everybody got basically how a SAT solver works? SAT solver is write your problem in propositional logic, then translate it to conjunctive normal form, which ought to be really easy, I'm sure. I don't think that way. I have a hard time translating it. Good thing I have an electronical computer to do the work for me. And the input and output formats aren't very human readable. These are solvable problems. So here's our core challenge. You gotta pass, the powerful tool is at your disposal, but the way you talk to it is hard. So how do you express your problem in a way that it can understand? So I wrote some utility functions that I will give to you. It's not a lot of code, but greatly improves your life. So one of them is called translate. It lets me write not P, Q, not P, and Q, the terms, and it translates it into what PicotSat understands. Presto, we get to use symbols. However, more importantly, we don't reason in conjunctive normal form. A lot of people think, and a lot of problems come in disjunctive normal form, so the ands and r's are reversed. So I would like to write the problem like this, which is how I think about it. So I've got a function from disjunctive normal form, convert it to conjunctive normal form. So this says, take the problem from the way I think about it, turn it into something that can be translated into the way PicotSat says it. And then there's a function called solveAll that takes care of the round trip and the translation. So our original problem is not P and QRR. Convert it from disjunctive normal form, generate all solutions, and there's the 5 solutions in a more human-readable format. The only problem is that P, Q, and R mean nothing to you. It turns out the symbols don't have to be letters. We can spell out words. Do you think that will be helpful?
Yes.
Fantastic. That said, this simplifies the working with PicotSat because you can work in conjunctive normal form and use symbols. There's one other problem. It turns out a lot of constraints don't even arrive in conjunctive normal form or disjunctive normal form. They arrive in terms of quantifiers. So our solution is to have some convenience functions. And I wrote 3 that let you express ideas in quantifiers. So the idea is max1 says one of these things are no more than one of these things can be true. It's possible for all 3 to be false, but no more than one can be true. So what that does is generate the conjunctive normal form for us. It is really tedious to translate this idea into this, especially if you've got a lot of variables. So this one expresses the idea, and this is just a straight pass-through, that at least one of these 3 are true. That one's not strictly necessary because it's a pass-through, but this one's far more interesting. How do you express the idea that exactly one of these 3 is true? Not 2 of them, not 0 of them, not 3 of them, but 1. And so that is much more challenging. And after a while writing these CNFs, you kind of learn to write this stuff out, but it's better to have a computer do it for you if you have more variables. In other words, if you have a problem that says, make sure that there's at least one of, or there is exactly one of A, B, and C, you enter 1, it generates this that feeds into the solver. Without these convenience functions, the problems that we're about to solve are hard. Also, I consider these primitives, and if you need to have higher level thoughts for your constraints, you should build on this idea and build your own constraints, way of expressing this constraints. These tools are incredibly painful to write out all of the constraints by hand. You really, really want the computer to do it for you. So, Sudoku, the promised Sudoku. They were floating around out here. Probably should have changed this one to match the one that they actually handed you out. Any of you work the Sudokus? Okay, my idea of fun with Sudoku is work one by hand first to get the idea, and then write a computer program to do the work for me. It will be not hard. So the idea is, given a puzzle like this, we need a way of entering it into a Python, and that is this is somewhat tedious. So I enter it into as a single string in row major order. So 8 blank 6, 4 blank 3. Here's the 8 blank 6, 4 blank 3. And the implicit string concatenation turns this into a single string. Our goal is to expect the computer to solve it and fill this out. I didn't solve this one by hand. The machine did it for me. So this is all of the code for the Sudoku solver. And one of the things that you will notice about the code, if you look at this later, is that very little of it has to do with solving the problem. Most of it is about taking this line and turning it into a statement of facts and of printing it out. So it's essentially the wrapper for it. So the interesting part is right here, which is generating the constraints. So here's the grid you're in. And so it loops over the table, all of the points and subsquares, and it generates all of the groups. The groups are every group of 9. So everything in the upper left 9 squares is a group. So that's all one group. Everything in this row is a group. Everything in this column is a group. It's everything that's competing with each other that has exactly 1, 1, exactly 1, 2, exactly 1, 3. So using this is fairly easy. Take the string, and we start with an empty conjunctive normal form. I want to be able to say, take each point and value and make a restriction. Every point and value can only be used once. Now, we want to make sure that every point gets, so that means that if you have a number 7, it has to get used in a group. You can't omit it. This one uses the 1 option again to say every value gets assigned only once in each group. So the number 2 only gets used one time in the upper left. And then the important part is the facts that we've known for the specific puzzle. The fact would be that the number 8 goes in this square. And so this expresses those facts, which is quite easy to do. And so we call the solver, and it generates the solution above. So is it fair to say that it's kind of handy to have the 1 in here? All right, a harder one. The Einstein puzzle. The theory is that, the story goes that Einstein posited this puzzle and said only 2% of the people in the population could solve it. Neither of these facts are true, but they make great lore. So the idea is this is a traditional logic puzzle. You have 5 houses in unique colors. The people who live in them are distinct nationalities. They each drink something different. They each smoke something different, and they each have a unique pet. So the Einstein puzzle gives you a handful of facts that seem unconnected. The person from the UK lives in a red house. The Swede keeps dogs as pets. The goal is to determine who keeps the fish. And the lore says fewer than 2% of the people in the population can solve it. I have given you a link to a nice write-up of how to solve it by hand. It isn't super easy, but it's not super difficult either. That said, what's my preference for how to solve it? Use a computer. And so when I dump it into my computer, it tells me where everybody lives. And it tells me the fish is in the greenhouse owned by the German who drinks the coffee. And so it answers all questions about that puzzle. So here's the code for the puzzle. I define the houses. I define the groups. Do you recognize these as being like the groups in the Sudoku solver? All of the groups of numbers that could go together? So that gives you a theme for how you solve these problems. You identify the competing groups. But then I built some higher level tools. How to express a fact that this person is found at that house. How to express the fact that 2 values occur in the same house. That 2 people are in consecutive houses and that 1 person lives beside another. So the idea is you use these tools to build the primitives to build higher level ways to express ideas. I have till 9:30, do I not?
We've been kicked out in 5 minutes.
You have until 9:30, and then we have to...
Okay, I have 7 minutes.
Okay.
All right, good enough. So I think this is, what I like is how directly this translates.
John Collins afterwards.
All right. So what I like about this is how well the problem translates directly into Python. This expresses the fact that the Brit lives in the same house as the red house. That the Swede lives in the same house as the dog, the Dane lives in the same house as T, that the White House is after the greenhouse, and that the milk is found in the 3rd house and the Norwegians in the 1st. One of the really great things about Python is that when you get to the point of actually encoding your problem, how directly it translates from the real world logic. Okay, so the part I'm giving you at the bottom is the utilities I wrote to humanize it, how to translate from the PicotSat forum, a front end for the iterator that calls the translator, how to express the ideas of a maximum 1, of just 1, and from a DNF. Interestingly, these concepts are high-level concepts. These are low-level implementations of the concepts. And if you're interested in low-level implementations, shoveling your data around, you need to get really good at iter tools because it makes short work of problems like this. If you know combinations, that's 1 short, fast line of code. If not, this is excruciating. If you know product, this is about 3 or 4 lines of code, but it can be made shorter and more compact with the little iter tools. So I'll give that one to you, and that is SAT solvers. How many of you like SAT solvers now? I didn't mention an application. So one of my clients is at layer 1 of the internet. So they're concerned about our printed circuit board has 5 layers that we can draw wires through. We have a bunch of components that need to be connected together. Those are constrained. We only have 5 letters. The wires can't cross each other, but they can go up a level and over. There's a limit on the amount of copper they can use, and there's some constraints about what signals can go next to each other without generating a crosstalk. And so they are wiring up very small boards, but have several thousand components inside and tens of thousands of wires. What tool do you think they use to figure out how to wire it together? Pencil and paper or a computer? A SAT solver. All right, there you go. And the last one is pattern recognition. I can go through this one very fast, which is good because we have no time. All right, the important topic, how to win at rock, paper, scissors. One of the things I love about Python is how easily this problem can be encoded. This dictionary describes the entire game. So rock, scissors looks up an RS is 1. That means that rock cut scissors is a +1 for the first player. The entire game definition is in this one line. Now that we've defined the game, we want to think about what? Winning, or more importantly, not losing. All right, so if you play randomly, it assures you can lose no more than 1/3 of a time, but you can't win more than 1/3 of a time. So that said, if our opponent is completely predictable, we should be able to win 100% of the time. In the real world, though, humans have a really difficult time simulating pure randomness. They have patterns in things that they do, try as they might to be random. So if I ask you to make 100 random selections in rock, paper, scissors, my bet is that I'm going to find some patterns in it that are unpredictable. That said, that's too difficult for me, so what am I going to get to do the work for me? An electronical computer. So several patterns are: a person has a mild preference for playing paper, or a propensity to select rock after they played scissors, or if we play paper, they always pick scissors after, because after all, scissors cuts paper, or they've got an aggressive strategy, they'll copy whatever we just did. The copying game is actually very easy to defeat. What we need to do is detect these things and then play to exploit that. So the logic is roughly this. For the number of games that we're going to play, we choose our move, get their move, figure out who those winner, update a history, and more importantly, a weight between strategies. So those of you with a machine learning background, you'll recognize this as reinforcement learning. And the particular algorithm being used is called a multi-armed bandit. And roughly it means you have 3 slot machines in front of you that have different payouts ratios to them. Some are more favorable than the others. How do you determine which is best? You start exploring, playing one at a time, and then in proportion to how well they pay you off, machines that pay you more, you play more. That is roughly the algorithm. If I had a little more time, I would explain all of the Python skills required to code this short and beautifully. But there's nice little worked out examples here. I'll give you the slides. They're self-explanatory. What does counter do? It counts. What does most common do? It tells you the most common occurrences. Zip star is a technique for transposing data. And when you zip a sequence to itself off by 1, it gives you digraphs. It gives you pairs of letters. So given A, B, C, D, it gives you A, B, B follows A, C follows B, which is very important in rock, paper, scissors, because people will have patterns of, I play rock, then I always play scissors. And this is new in Python 3.7. You can make a weighted choice from a population, given some weights. So given rock, paper, or scissors, choose them in a proportion 6 to 3 to 1. All right, the code for it is fairly short. The game definition. Some utilities for making our strategies, which is given some events, pick the most common one, or given some events, pick them in proportion to how often they occur. So you can choose proportional or choose the most common. So your strategies are guess randomly. You should always include that in the mix because what if your opponent's smarter than you? This is the one that you need to default back to. If they're better at recognizing your patterns than yours, this is one you want to be in the mix. So this is your defense. If you start losing, this is the one you come back to. So each one of these says, if I got a single event rock, just count how often it happens and play in proportion to that. On the other hand, the greedy says, if the person mostly plays rocks, always play rocks. A digraph is, if their most recent play is S and they usually play R 2/3 of the time after, respond with that same proportion. And the greedy says, just always do the P. So I made a list of the strategies, and this code is our pseudocode before. Choose a move, so it loops over our strategies. Choose one of the strategies in proportion to its weight, the ones that pays you the most. Get our move, get your opponent's move, determine the winner, print it out, update our history and weights, and loop back and print the summary score. And I really, really wanted to run this for you, but I look like I'm about to actually be forced off the stage. I'm being mowed down. But we had to have a raffle. They told me an hour. I didn't get an hour. All right, so this is the human player. These are various opponents. So you define your opponent, run it. And when I run it, the very last one is you playing versus the machine. And so I challenge you to try this, set it to 100, play rock, paper, scissors with my machine, and see if it can figure out your patterns. It'll tell you which strategy it's using, by the way. One more thing. That's not fair. That's just me. The important part of this is not that it plays rock, paper, scissors. It's that all of that code was 100% generic, not unique to that game. So the same logic applies to other strategy in other games. A very simple modification is rock, paper, scissors, LizardSpock. And in fact, this is a generic machine learning algorithm, reinforcement learning with one-armed bandit. Every toy that I showed you tonight has real-world applications. I hope you enjoy the code. Thank you so much for coming. Have a good night.